Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture on vibrational spectroscopy. In the previous lecture, we are discussing vibrational spectroscopy in polyatomic systems, where we started using normal mode description for polyatomic systems. We also use symmetry argument to define the symmetry property of different normal modes of water molecule. Just to recall the important part of the discussion, we would see here that this shows the water molecules normal modes of vibration. There are 3 degrees of the 3 normal modes for water molecule. One is symmetric stretching, the bending and asymmetric stretching, and we also discussed the character table corresponding to the water molecule. The water molecule belongs to C2b point group, and this is the character table that you can find in many textbooks for C2b point group. For other molecules with other symmetry, you would find this character tables for other point groups as well. But some of these discussions that we are going to do in today's class are in general, we are just using water and C2b as an example, but you can very well extend this analogy to any other molecule, any other character table. We also discussed that different normal modes of water molecule can be assigned a particular symmetry. For example, symmetric stretching belong to A1 symmetry or A1 irreducible representation. Bending also belongs to A1 irreducible representation. Asymmetric stretching on the other hand belongs to B2 irreducible representation. Now, we will continue our discussion further on this point, and we will see how we can use symmetry to derive selection rules. Since we are discussing the vibrational spectroscopy, so therefore, the intensity would be given by this transition dipole moment, which is given as psi final mu psi initial. So, this is the initial state psi initial going to the final state via the electric dipole moment operator, which allows the molecule to interact with the electromagnetic radiation and shows this transition to us. Now, under symmetry, when we incorporate symmetry argument, one particular thing that we have to remember, of course, I am aware of the fact that some of you do not have a formal group theory course, but I am trying to give you the basic information that you require to understand our discussion, but things will be much more clearer when you have if you have a formal course on group theory. Now, to one thing that we would keep in mind here is that each vibrational state will have a symmetry. So, suppose I call this symmetry of final state as gamma final, the initial state symmetry call it as gamma I, or the symmetry or irreducible representation corresponding to initial state and final state, and the electric dipole moment, the operator, also has a symmetry. So, what happens is that we would to derive the symmetry selection rule, we have to ensure the direct product of these 3 irreducible representation or these 3 symmetry levels must contain the totally symmetric irreducible representation. What is totally symmetric? The totally symmetric in C2v representation is simply A1. As you can see, it is symmetric with respect to each symmetry operation in this group. A2 is not symmetric with respect to these 2 operations, B1 is not symmetric with some operations, but A1 is totally symmetric with respect to all symmetry operation of the group. So, therefore, we have to find out that the direct product of these symmetry levels or this irreducible representation must contain A1, either become A1 or in other groups you would see that it can have more, or it should contain A1 or should become equal to A1. Now, let us do our discussion. How do I obtain the symmetry element of this, let us say each of these terms. First we will discuss about the operator part. Mu, for the electric dipole moment operator, the gamma mu, to get that we have to see that electric dipole moment operator symmetry is proportional to the translational symmetry, which are defined in this character table as x, y and z. So, you see that mu has 3 components, mu x, mu y, mu z. Suppose if I use only z polarized light, the electromagnetic radiation will be effective only along the z axis. So, therefore, it would be mu z would be the complete representation of the electric dipole moment. So, for different either z polarized or x polarized or y polarized light, I would have action of mu x, mu y or mu z, but for a general for ordinary light, when it is not polarized along particular direction, of course, mu x, mu y, mu z, all 3 are simultaneously operative. So, to make the discussion general, the symmetry element of the electric dipole moment operator is given z x y, z is a1, sorry, x1 is x is b1 plus x2 y is b2 and z is a1. So, this is the symmetry element of mu z, this is mu y, this is mu x. Now, this is for all other character tables, you have to look at the symmetry of electric dipole moment operator, you have to see where z, x, y are written, and then you have to write down this corresponding irreducible representation. So, we obtained for the operator part. Now, let us look at the how we can obtain the symmetry of a particular vibrational state. Well, for a polyatomic molecule, you know that I can define the ground state, psi ground state, as where all the vibrational modes are at their lowest level. The lowest level is V equals 0. So, this is the ground state of the polyatomic molecule, where along each mode the molecule is at the ground state. This representation has the symmetry of A1 or the totally symmetric. So, the ground state, since it has got no excitation along any mode, it has got the total the symmetry of the totally symmetric. Now, consider one particular vibrational state where I am exciting only along one particular mode. What will be the symmetry of this state? The symmetry of this state will be, I see that in all other states, all other modes, the vibrational state is the ground state. So, therefore, each of them contributes A1 to it. Only along Q1 I see one excitation. So, therefore, the symmetry of this one this state will be gamma of Q1. Whatever the symmetry of Q1 mode is, that will be the symmetry. For example, if you recall our discussion, for water molecule, the symmetric stretch was having the symmetry of A1. So, therefore, this would, if Q1 is symmetric stretch, so this would have been A1 symmetry. So, the symmetry of this state would psi would have been A1. If Q1 would have been the anti-symmetric stretching of water molecule, then we know that particular degree of freedom showed B2 symmetry. So, therefore, the symmetry of that state would have been B2. So, if I say that a state which is 1 1 0, what would be the symmetry of this state? This state symmetry will be gamma of Q1 direct product of gamma of Q2. So, if this is A1, this is A1, then I will multiply A1 with A1, you would see that A1 multiplied with itself will give you A1. If gamma Q1 is A1 and this is B2, then I will multiply A1 with B2 and so on and so forth. So, therefore, for any vibrational state, I can determine the symmetry of that particular state. So, I know now how to get the symmetry of the initial state, how to get the symmetry of the final state, how to get the symmetry of the dipole moment operator. When I make a direct product of this, I should get the totally symmetric representation. Then only this particular transition will be infrared allowed or IR active, otherwise it is not. Now, let us take an example. Suppose we consider now for water molecule. Now, so far our discussion was in general. So, suppose I am considering water molecule, I am going from 0 0 0, that is the ground state of water molecule, to 1 0 0, where the Q1 mode is excited by 1 quantum. So, let us find out the symmetry element of this the final state. The symmetry element of the final state is, it is excited only along symmetric stretching Q1 mode, whose symmetry is A1. So, therefore, A1 raised to the power 1, which is simply A1, multiplied by the dipole moment operator. Dipole moment operator, I know this is B1 plus B2 plus A1, because if it is a mu x, mu y, mu z, and the final state, since it is the ground state, I know this is A1. Let us now find out what happens to this product. So, I can see that since the second term has 3 terms in between them, so I can rewrite them as A1 B1 A1 plus A1 B2 A1 plus A1 A1 A1. Now, let us look at A1 cross direct product B1 with A1. To get this direct product of A1 B1, you simply have to multiply these numbers with the B1 numbers. So, 1 into 1 gives me 1, A1 into minus 1 gives me minus 1, 1 into 1 gives me 1, 1 into minus 1 gives me minus 1. So, the direct product of A1 into B1 is 1 minus 1 1 minus 1, then I see 1 minus 1 1 minus 1, so this is B1. So, therefore, I conclude A1 cross B1 is A1 cross B1 is B1. So, since A1 cross B1 is B1, similarly in similar way you can do this. So, you would see that the result of this will become B1, the result of this would be B2, the result of this would be A1. So, the mode is infrared active only when it contains totally symmetric representation. Does it? I see yes, because it has A1 in it. So, therefore, this mode, this excitation is IR active, but I would have to see this, that I am getting this A1 only along Z direction. Because of mu Z, I have this transition possible. So, therefore, to make this transition more effective, I can simply, if I use Z polarized light, I would see this transition, but if I use X or Y polarized light, I would not see this transition. But if I use general light without any particular polarization, of course, I would see this transition, but I know that it is the Z component of this electromagnetic field that is inducing this transition. We would do this for one more example, 0 0 1 mu 0 0 0. So, that means it is excitation along the third mode. You would see that the symmetry of the final state is B2, because Q3 has a symmetry of B2. This is what we derived in the previous slide. Direct product mu has 3 symmetry, B1 plus B2 plus A1. Direct product, the ground state is A1. So, when you expand it, you would see that when I multiply B2 with B2 and with A1, only this term will give me totally symmetric representation. So, therefore, this transition ground state to first excited state along Q3 mode is allowed transition, but this happens along the Y polarized light. Which is obtained here. So, this indeed contains gamma 1 in addition to A1. In addition to A1, it will also have other terms. So, you can obtain the other terms. So, now one thing that you must remember is that this particular transition is allowed. So, now we are saying that there is a general feeling that since if I am talking about the fundamental transition, that means I am going from 0th level to first level along a particular mode, my ground state is becoming totally symmetric, and the final state has the symmetry of that particular mode. So, therefore, if my electric dipole moment contains one of these electric dipole moment contains the symmetry element that belongs to the mode that I am currently exciting, then only this will be IR active, otherwise this will not be IR active. We can have a general statement to that effect. It says that for a fundamental transition to be infrared active, the corresponding normal mode must belong to the same symmetry species as one of the components of electric dipole moment. So, I can immediately find out the electric dipole moment representations. So, either B1 or B2 or A1. So, if there is a normal mode which has B1 or B2 or A1 symmetry, then for that normal mode the fundamental transition or 0 to 1 is allowed. Which one is missing? You can see that A2 is missing, because A2 the electric dipole moment does not contain A2 representation. So, therefore, of course, in water molecule we do not have a symmetry, we do not have a normal mode whose symmetry is A2. Suppose we design a state which has symmetry of A2. In that case, the fundamental transition will not be allowed, because electric dipole moment does not span that particular irreducible representation. So, this general rule becomes very useful. You can practice this rule by looking at the character table of other point groups and then see whether this holds or not. Okay, we now we discussed about the fundamental transition, that means going from 0 to 1, but we also know when we allow the higher order electric dipole moment terms, then overtones become allowed. So, let us look at one example of an overtone. So, suppose to have an overtone, I have something like this. So, I am going from V initial 0 to V final 2, and of course, the electric dipole moment is over here. Whether overtone is symmetric infrared active or not, to obtain that we can also use the same argument. Suppose consider water case, the example that we are currently having. So, suppose I am considering 0 to 0 mu 0 0 0. Is this transition allowed or not? To obtain this answer, we again do the same thing. We find out the symmetry of dipole moment, that is we already know B1 plus B2 plus A1. The initial state, since it is the ground state, it has total symmetric A1. This state 0 to 0 is excited by to V equals 2 along Q2 mode. So, therefore, I will have to find out what is gamma Q2 and then take its square, gamma Q2 into gamma Q2. So, since if you remember, gamma Q2 is the bending mode. So, it had symmetry of A1. So, therefore, A1 direct product of A1 gives me A1. So, therefore, the symmetry of this state is A1. And when I take this direct product, I can see that A1 is there on both sides. So, therefore, only this component, the mu z component of the light would contain A1. So, of course, this transition is allowed, but mu z would be the driving force for this overtone transition. So, even for overtone transitions, we can also use the similar argument. I would just give one example of a combination band. So, you remember when I say combination band, what do I mean? Suppose I have 0 0 0 to 0 1 1. That means, I have gone from excited both Q2 and Q3 mode. I know. So, in this case again the rules are same, mu 0 0 0. What will be the symmetry of 0 1 1? I see that it is excited along Q2 mode, excited along Q3 mode. The symmetry of Q2 mode is A1, symmetry of Q3 mode is B2. So, therefore, the final state has this symmetry. Direct product of the operator, which is B1 plus B2 plus A1, direct product of A1, that is the ground state. Now, A1 into B2, when you do this calculation, you would get B2 . So, you see that B2 into B2 would give me A1 and A1 into A1 would give me A1. So, therefore, this also contains a total symmetric representation. So, therefore, this is an allowed transition and it will be the Y polarized light that will induce this transition. So, this way we can see whether a fundamental band is allowed or a overtone is allowed or even whether a combination band is allowed. The rules, so you can see that for using symmetry arguments, it is very easy to find out which modes are allowed, but of course, symmetry will not tell us what would be the final intensity of it. For that, we have to obtain the first derivative and second derivative, as the case may be, of the dipole electric dipole moment operator corresponding to that particular normal mode. We will now discuss one very important issue, is that what is the effect of anharmonicity and in particular the mechanical anharmonicity. Remember, we defined our normal modes by truncating our potential energy to the second order. We said that this is within harmonic approximation. We had this in one dimensional case, the potential was half k x square, and in polyatomic cases we truncated our potential energy exactly at the second order expansion. But if we continue to treat the higher order terms, of course, you will have many more terms. Now, the normal modes that we normally derive are within this harmonic approximation. That means, the potential is harmonic oscillator type of potential. So, the normal modes are defined according to harmonic potential of the harmonic oscillator potential. So, therefore, the normal mode that we obtained and we liked because they were decoupled from each other, we could treat one normal mode at a time. That decoupling is strictly valid only when we have this harmonic approximation valid. The moment we go beyond harmonic approximation, that means we consider the higher order terms in the potential energy expansion, then these normal modes no longer are the true solution of the full potential. So, therefore, they would start interacting with each other or they would start interfering with each other. In often cases in real life molecular spectroscopy, you would see cases where the effect of this mixing of normal modes appear in the spectra. A few examples are we will discuss, or at least the principle behind those examples we will discuss, and in one thing that becomes very interesting is what is called as intensity borrowing. So, this is an effect of mechanical anharmonicity, not necessarily not because of electrical anharmonicity. Electrical anharmonicity comes when you allow the higher order electric dipole momentum. So, that is how we get the overtones, we get the combination bands, because we have allowed the second order terms. Mechanical anharmonicity causes this intensity borrowing. Such that we know that the fundamental transitions carry maximum intensity, they are the intensity carrying transition, they have the largest intensity, whereas the combination bands or the overtones, they do not carry intensity or their intensities are much smaller, because you see that they are higher order effects. So, therefore, the coefficients that come before the integrals are the second derivative terms. So, they are much smaller. So, therefore, their intensities are going to be small. But in some cases what happens, we see that the intensity of a fundamental band has gone to either a combination band or to an overtone band. How that can happen? We will look at two examples. The first example considers how we can see that a fundamental band intensity can go to the combination band. In this particular example, there are three different normal modes considered here: A, B, C. Along A mode, the vibrational states are shown here. This is the ground state of A along A mode. This is the first excited state along A mode. So, to go from 0 to 1 along A mode, you require this much of energy. This is the energy difference. Now, along B mode you see this is again 0 state, the ground state, this is the first excited state, this is the second excited state, this is the third excited state, and this is the energy corresponding to B mode. So, the fundamental transition along B mode would occur at this energy. Now, the third mode C has 0th level here, first level here. So, this is the energy along the C mode. Now, you see there is an interesting situation. This transition that you see 0 to 1 is a fundamental transition. So, this is the total ground state. So, 0 0 0, it goes to this transition as 1 0 0. This is the fundamental transition, therefore, it has good intensity. Now, this transition occurs at energy E A. Now, let us look at this situation. If I consider a transition 0 0 0 to 0 1 1, that means along B mode first excitation, along C mode first excitation. In this case also, if you add E B and E C, this will be very similar to E A. When such a similarity of energy occurs, if the potential is anharmonic, which is often the case, in this case since E A is very close to E B plus E C. So, therefore, the fundamental transition and the combination transition both occur at the same energy. So, therefore, the states get mixed, and as a result what happens, the intensity of this fundamental band gets transferred to this combination band. So, there is an intensity borrowing from fundamental to combination when this situation arises. So, these resonance conditions, which are accidental resonance situation, where energy of one fundamental transition becomes nearly equal to the energy of another combination band. But the combination band should ideally have low intensity, but in this case, because it borrows intensity from a fundamental transition, which also happens to occur at the same energy. So, therefore, the intensity of this combination band suddenly increases. So, when we see such effect, we know that mechanical anharmonicity is at play. There is another example here. Instead of combination, we will look at the fundamental to overtone. For example, here it is showing only 2 modes. So, this is the ground state 0 0. Along A mode, we have 0 1 2. So, you see this is the energy along E A. Along the B mode, this is B. So, for 0 0 to 0 1 transition, which is actually a fundamental transition along would have occurred at E B, and since this is a fundamental transition, so it will have good intensity. But in this case, along A mode, if I go from 0 to 2, you would see that twice E A is equal to 2 B. So, in this case, this overtone along A mode happens to have same energy as the fundamental along B mode. So, this is again another resonance where accidentally the B mode's fundamental band appears at the same energy as the overtone of A mode. In this case, what happens, even we know that overtone transitions should have ideally very low intensity, but since it overlaps with another fundamental transition, so the intensity goes from the fundamental transition to the overtone, and this feature is expressed in terms of this Fermi resonance, where the fundamental transition along one mode becomes accidentally degenerate to an overtone of another mode. In that case, the intensity transfer occurs through the Fermi resonance process. So, in this lecture, this is where we would actually conclude our vibrational spectroscopy. We see that for vibrational spectroscopy of polyatomic system, symmetry plays an important role. By using symmetry arguments, we could derive the selection rules for different normal modes of a molecule. Of course, in this lecture, we restricted ourselves only to C2V symmetry. Once you are more familiar with point group symmetry, you can use the same argument to apply it to any other molecule of your choice. Thank you for your attention.